Welcome to Circuit Valley. I'm Gaurav. This video is the third part of our ongoing series. I'm going to show you how to use a modern oscilloscope, decode function of a modern oscilloscope to decode different type of communication protocol on an embedded environment. Last two videos which I published, first video we covered in depth of SPI. Second video we covered in depth of I2C, how to set up a decode, how to set up a trigger, how to set up a bus trigger, how to clean up a trigger and use advanced trigger. In this video we're going to look at RS232/UART. And you can see on the front of your screen there are three oscilloscope setup as per the last experiment. On the right side you have RTB2004, in the middle you have MSOS 804A, and in the left side you have MDO3000. So these are three different families of oscilloscope, totally different class of instrument, totally different age of instrument, and we are going to cover the decodation and handling of a UART signal in the embedded environment using an oscilloscope. Setup is exactly same. We have this little FPGA board which I showed you in the earlier video. If you want to get to know this board, you can look at my previous videos, and this board is going to help us generating UART signals. First we are going to try and decode setup with RTB2004, a modern oscilloscope from Decode. Second we will try to decode with MDO3000, a 500 MHz, a relatively one generation older oscilloscope from Tektronix. And third we will switch to my 8 GHz MSOS 804 from Keysight. You can see all the oscilloscopes are connected to UART and RS232. Both of the buses are outputting the same thing. RS232 and UART are basically same protocol. There is an only difference of voltage level and physical characteristics. Other than that, timing wise they are exactly same. I'll show you in a second what's the difference between them. So all of the oscilloscopes are currently connected to the UART and RS232 output from this FPGA. So right now on your screen you can see the web view capture of my RTB2004 overlaid onto the screen itself so that you can have better contrast and you don't struggle with the reflections and everything else. On your screen you see there is some kind of activity going on the channel number 1 and channel number 3, and you see both of the channel. Let me zoom in a bit. Both of the channels, maybe I'll do a single capture, you can see better. It appears to be both of the channels are having same signal, but the yellow signal is going from, let's measure it, going up to 5 volts, and this brown signal which is on channel number 2 is going minus, I do not know how much it is, let's measure it. So it's going around minus 7 volts or minus 8 volts to plus 8 volts. So it has around 16 volts of peak to peak signal. If you want, I can show you how to set up a measurement, quick measurement. Okay, so it is around 8.7 volt top, 8.7 volt down there, and that's how the signal is. Okay, and the upper signal was around peak 5.6 volts and bottom was minus 3.92 volts. You can assume it to be a 5 volt signal is perfectly fine. Let's remove the quick measurement, and now we are back onto the screen. So this oscilloscope also have this quick measurement feature, so you can quickly measure what you want to measure. So you see there's a stark difference between the both of the signals. The upper signal is the UART signal, okay, which you normally know as sometimes as TTL, and it can be sometime instead of 5 volt, it can also be 1.8 volt, 3.3 volts and stuff like that. The signal on the bottom is the RS232 signal. This is the signal which you will see going over to the lines of relatively longer transmission lines of RS232 and stuff like that. This RS232 offers advantage of a little bit more noise immunity and everything else. It can also be transmitted over long lines, and you can see it's also inverted from the primary signal. The UART sends some signals, and there is a RS232 transceiver which inverts it and amplifies also the voltage. And one more thing you need to notice, that ideal voltage of the UART signal is 0 volts, while ideal signal of this RS232 is minus 8.7 volts. So let's zoom out a bit. First of all, as I said, always when you are dealing with the oscilloscope, you need to find a way to trigger statically or trigger exactly when you want to trigger. This kind of trigger that it's jumping around, it's not acceptable. You cannot deal with this kind of signals, and one basic method to deal with digital stuff is setting up a pulse trigger. So let's set up a pulse trigger. Let's do a single capture first. Let's measure how much pulse is there between both of the bytes of transmission, it's around, you see, supposed to measure here, not up there. That shows you position. Delta is around 2 milliseconds. So we will zoom out a bit. I will see if there is any other gaps coming between them. Okay, so you see there is one more gap coming in, and I will zoom in using the zoom button. I'll keep you updated so that you can follow along. Okay, and we'll take our mouse. This oscilloscope supports a mouse, and I'll drag the zoom window, and I'll bring my cursor here. Okay, you can do set to trace, but these cursor are a little bit finicky in RTB2004. We need to find out where the second cursor is. Second cursor is somewhere down there. Yeah, it is not on the trace. Maybe I can set it up using the cursor menu, and I'll do set to trace one more time. It is set to source channel 4, should be set to channel 1. Let's do set to trace one more time. Now it has come to on screen. Generally oscilloscope have a button which called bring to screen or something like that. I'll show you on my MDO3000. There is a button called bring cursor onto the screen, so you don't have to struggle and find out the cursor, where the cursor is. Somehow we managed to bring it on the screen, otherwise it will take a lot of struggle. So you see, in between individual bytes, there is a dead time of around dead time around 4 milliseconds. And if I zoom out, these individual packets, they have between them, individual bytes, they have between them around 2 milliseconds, and sometimes you see a little bit more, and we generally look for this kind of situation. And you see the delta down there, and delta has 3.2 milliseconds. I'll set it up, the trigger around 3 milliseconds of a pulse width trigger, and we will be having a stable trigger then. So instead of edge, a width trigger, and you see it's a positive going pulse. If you're triggering on channel number 3, then you should be setting a negative going pulse, and I'll set it to maybe 3.1 milliseconds. Okay, I'll let it run. So by triggering on the appropriate position, you can see the oscilloscope is running and it's capturing new waveforms, and we have a rock solid trigger. We just found out a trigger condition for ourselves, and with the appropriate trigger we found a rock solid trigger. Okay, and if you want, I can show you what happens when you trigger somewhere here in these pulses. Let's measure one more time. Okay, so it is also 3.1 milliseconds. Okay, so we will increase this time, increase our criteria of trigger time to above 3.2. Oh sorry, we will decrease it to maybe 2 milliseconds or something like that, so that it can find everywhere trigger between the bytes. So the bytes do not flicker. We do not trigger in a byte, but we do trigger in a packet. So you see the byte themselves change because the trigger condition is such a way that it can trigger almost anywhere, but it will not trigger. It's a little bit better than edge trigger, but it is still worse than the packet trigger. So we'll change the trigger one more time back to our, maybe like this time we will have majority, so we'll change to 3.5 milliseconds. Okay, and we again have a rock solid trigger. So now when our trigger is stable, we can set up a decode. I'll go and call up a protocol menu, and I'll select UART. Okay, and we'll configure. It's on, generally UART allows you to 2 buses, RX and TX. If you want to decode both of them, we can decode both of them. If you want, I can show you both of the triggers, both of the channels being decoded. But you need to watch. What you need to watch is that, look at this voltage level, this high low you see right next to the C1 C3. This says high or low because these C1 and C3, UART and RS232, both have opposite polarity to it. So this oscilloscope somehow doesn't allow polarity inversion for one channel or another channel. It couples them, both of them together, So that's where we have problem. And you see on the right side, the little waveform which you see on your screen, which shows start bit going idle. When I change the polarity, you will see it changes. Okay, so we will not be able to decode TX and RX both at the same time. So I'll disable it, set the polarity to high, because this is how our bus is. Bus ideal is high, not low, and then the first bit goes low. Parity is none. Okay, bud rate we do not know, so that I will show you how to define a bud rate, or how to find a bud rate, and we will let it decode, and I'll show you that it will not do much good of a job because our bud rate is wrong. Okay, so let's go in there and try to find out the bud rate. Okay, so how do you find a bud rate? Bud rate is the invert of the time of one bit. So you just take your cursor, measure how much time it does it take to transmit one bit. Generally, if you have enough packets, you can determine how much is one bit, or if you are really in bad luck, you can measure the whole byte. Generally, you will have one start bit, one stop bit, and no parity bit, but after trial or 2-3 trials, you will definitely can find out bud rate of an unknown signal. So this is, one packet is 10 bits normally, can also be 11 bits, and you take the whole byte time and divide by 11, and you see the bud rate. So you see delta is 1.104 microseconds down there in the window, and bud rate is, I believe it is close enough for 9600 and 9600 bud rate, and we will set there. Configuration. This oscilloscope somehow has predefined buds, so we don't need to do much, and it is already selected for 9.6. So you see this data is A, is already decoded. If you want, I can zoom in, and you see start bit come, data A0 come. Let's look at the stop bit as well. Stop bit also came. Okay, so these are the tricks. I found out the bud rate without without having the previous information about it. So this is very basic stuff, and let's zoom out, and you see this packet looks some kind of text or something like that, or some other value. So what we will do, I'll go in the UART and I'll go bus, and I'll say display setup, and instead of hexadecimal I'll change it to ASCII. Okay, so now you can make sense out of it. Maybe you can make sense out of it, that which company this board with our FPGA board came from. Okay, so you see that here where my cursor is right now, Tektronix, it's going to say Tektronix. This is just a text. If you want, I can zoom out and we will look at the bus table. There it will be visible a little bit better. Okay, it's say Tektron. Zoom out further. Okay, let's see what does it say. It says Tektronix Engineering Innovation. Okay, Tektronix Engineering Innovation. This is the bus content R, and we are happily able to decode the bus. We set up a nice appropriate trigger for this bus, and we can easily decode it. It was very easy. So now next is we will set up a trigger based on the message itself, so that we can learn how to set up a data trigger as well. And let's go to the trigger menu. It must be up there, trigger, and instead of width trigger we will do serial bus trigger, and you can see it's already detected that UART bus is being used. If you want, you can set up a data trigger, and then it will trigger exactly on data. And first of all, we need to find out what is that data. If you remember, its message says Tektronix and Engineering Innovation. I do not really know what does T's hexadecimal value is. So maybe I'll zoom in. First of all, I need to get the, or maybe I can type, what do you call it? I can type ASCII. I cannot type ASCII. I can only type hexadecimal. So this is one also little feature of this oscilloscope. This allows you to trigger on 4 symbol pattern, and you can choose any combination of those 4 characters or 4 hexadecimal words or 4 bytes, and we just need like 1 symbol. I'll be more than happy with 1. If you want, you can leave the value XX, and maybe we'll take 2 actually. We will trigger on TE, and let's close it, and let's go to the protocol menu and do the bus display. I'll do bus display hexadecimal. Okay, let's do bits I'm not interested in. So hexadecimal, this is T, 54 and 65. 54 is the hexadecimal for T and 65 is ASCII hexadecimal for E. So we will now go to trigger and 54 and 65. This is what we're going to set. Okay. 5 4 6 5. Now let it run. I'll turn off the bus maybe, or turn off this thing, and we will zoom in where it's triggering. Is it even triggering? Okay, let me get the trigger point on the screen. We need to change the bus display to ASCII so that we can see it's really triggering on tech. Okay, it's not triggering. I'll do a force trigger, and you see it's supposed to trigger here after T and E, but it's not triggering for some reason. Let's look at the bus display one more time so that we can look at the content. I'll change the type to display type to hexadecimal so that I can see it better. So 54 and 65. Yeah, it's 54 and 65 hexadecimal. Okay, let it do in the hexadecimal, and we'll go to the trigger menu one more time and see if we set up something wrong. So we are triggering on 5465 hexadecimal, and our threshold is also right. Parity none, stop bit none, by baud rate predefined. UART trigger, it can trigger on different things on UART: start bit, frame start, frame stop, symbol, and pattern. What does symbol do? If it finds any symbol at all. Okay, pattern. And it somehow doesn't detect this pattern. Or does it have to be other way around? 6 5 5 4. No. 5 4 6 5. Let's do a one single byte capture. Then we will see one symbol only. So now it's triggering 54H. You can see the hexadecimal 54H. This is the symbol for T, and it's triggering exactly where it's supposed to trigger. If you want, I can zoom in. I think this is also a pitfall for young user. This is my assumption. You see this bracket there, this little box? Because this packet is arriving quite late, it is not considering it as a packet or symbol which is consecutive, and that's why it cannot trigger on it. Okay, so number of symbols, pattern, most likely that is what's causing the issue, that it doesn't like any symbols. Break, start, stop, pattern. This is also same thing. Any symbol, you can say pattern, and now it stopped triggering. I believe this is the culprit, because it doesn't see the packet coming so early enough, and that's why it just says that this is not never coming, and that's why it cannot decode. So this is one way of taking it. Not frame start, we will take pattern, and we will just take symbol, one symbol. Okay, one symbol. So even with this fancy oscilloscope, it has features which sometimes fold you in the pitfall. So now you can see you're triggering on exactly same T or Tektronix. I will change the bus view if you want to. Display setup, and I'll say ASCII, and you are triggering on Tektronix. So we have successfully proven that RTB2004 can happily decode UART. We can easily find out the baud rate, set up appropriate trigger for the UART signal, or set up a appropriate trigger for the any signal for that matter. This oscilloscope can also trigger on the data, trigger on symbol, trigger on start, and stuff like that. I think this enough for RTB2004, and I'll move to now MDO3000, and there you will see what do we see there. So now we are at MDO3000. It is also in default trigger state. It looks a little bit better, and it's triggering on the falling edge. And let's look at the sample acquisition depth. It is around acquiring 100k sample in acquisition. So this oscilloscope is a little bit different, behaves a little bit differently, and we need to set up the trigger first so that this flickering of waveform disappears. And you see the same stuff you see in this oscilloscope as well. There is a gap of a packet, and this oscilloscope does not have touch screen, so I cannot use it, but it has decent cursor. And I showed you there is this button is called bring cursor onto screen, and this button is really helpful. Sometimes you have it, I'll show you how does it work. You have off the record, something like this. The cursor are not on the screen, and you can just say bring cursor onto the screen. Cursor will be on the screen, and live would be happy. This kind of feature makes your oscilloscope usage very easy. So you see that gap which we determined, that's the gap between two Tektronix innovations packet. Its delta is around 4.4 millisecond. We will set up a width or pulse trigger 4.4 millisecond, and we will see how does it look. Measure, not measure, we'll go to the trigger menu. We will set up a pulse width trigger, and we'll need a positive going pulse, and the pulse need to be greater than around 3.5 milliseconds. So now let it run, and you see trigger is rock solid, and you see the trigger is absolutely solid, and there is not even a single movement. Even I'm looking at the packets later, there's a minute movement, but UART allows these kind of stuff. But this will not hinder us from decoding this signal or analyzing it for the sake of our enjoyment. This is absolutely rock solid trigger, and let's zoom out and let us set up a decode. This is bus decode. Set for I2C, we will change to RS232. Define input. So this is the baud rate 9600, 8-bit, none parity, packets on another packet. We do not have packet any. It can define the packets as well. And then threshold is around 2.1 volt. We'll analyze how much is it. Yeah, it's 2.5 volt should be appropriate. And there must be something else wrong as well. Define threshold. Let's zoom in a bit so that our UART is showing us a framing error, but I did not enable framing. Okay. Define inputs. TX is on, it doesn't matter. Polarity is normal, polarity is inverted. Now, okay, that was the problem. Polarity was inverted. Let's zoom in on individual packets. So packet starts with A, 20, 54, which we know from ASCII is T, E, Tektronix, and we will so bus display. We'll do ASCII. Somehow this oscilloscope allow you to view ASCII in this UART, and you see it says Tektronix. If you want, I can capture more data. And now we zoom in. Okay, in this kind of case, it's a little bit more than what I anticipated. We will increase the record length to 1 meg. Okay, and now we will look at the bus display rather than looking at the waveform itself. So it says Tektronix line feed enabling innovation or something like that. Let's event table, enabling, innovations, line feed, Tektronix, enabling innovation. So this message, Tektronix enabling innovation, getting repeated, and this is what's being displayed on the bus. If you want, we can decode the other signal as well. So define input, instead of channel 1 you choose channel 2, and there the polarity need to inverted, because as I said, the signal, even though different voltages, it's just inverted polarity. Signal is same, it says Tektronix enabling innovation. It's as easy as that. There is nothing much going on in there. And if you want, maybe you can look at the framing feature of this oscilloscope as well. Let's look at the last byte. Let me zoom in and find out what is the packet end. So framing is also helpful. You remember we were not able to trigger on 2-byte pattern. That is most likely due to framing. So it's end with a non-ASCII displayable character. So we'll go to bus menu, event table, or maybe bus display, will go hex. So 69. Okay, I think the 69 may be appearing somewhere else as well, but we'll look at the bus table. So 69, yeah, it appears many times in the signal. Okay, maybe I'll set up a decode or framing on this character A. Okay, let's do a framing. Clear. This is packets on A. Okay, and bus display need to be ASCII. Yeah, so this is how the easy framing is. You see this framing is enabled, and you see the message in your screen. Tektronix is being displayed together. Tektronix enabling innovation. And if you go to the event table, you will see exactly the same thing. Tektronix line feed enabling innovation line feed, and there is no more there's no more data there, so there's nothing more getting displayed. So as easy as that, and framing helps a lot. And if you want, we can try to set up a bus trigger on this oscilloscope as well. Yeah, this DVM conflict, when the DVM is getting sourced, then it cannot go to the video trigger or something like that. But it's not a problem. It's just the way I have set up my oscilloscope right now. So bus RS232 trigger on. This has these options: start bit, RX start bit, end of the packet. Okay, and stuff like that. So we will do TX data, because this is the TX bus. Data is, you remember, we can select 54. I think I can enter it. No, I cannot enter it. I have to put it through the keyboard. So we will trigger on tech. Maybe we'll set it to 2 bytes. Okay, so now I have to carefully enter the value. Need to be 5, 4, 6, 5. So we'll trigger on TE. Okay, same thing which we try to do without framing there. Let's get the trigger into the. I need to disable the framing for that, because otherwise you will not be able to happily see what I'm triggering on. Like I can show you, the T point of me is the second byte, and we are exactly triggering where we're supposed to trigger, but it is not being displayed because we are not in the bus display mode. Packets off, and you see the T is exactly after TE, which is 5465. If you want, I can show you the hexadecimal. 5465 trigger is absolutely rock solid. We are triggering where we're supposed to trigger. So with this oscilloscope also, we were able to find our packet, make the sense out of it. We decoded both RS232 and UART signals, and there is only the polarity inversion between them. There is nothing else. Only the voltage level is different, and we were able to set up a decode. We were able to set up a frame, and we were also able to set up a message-based trigger. I do not know how many words it allow. Let's see how many maximum word it allow, because you remember our current other oscilloscope allow 4 bytes, and you can set here 10 bytes because it's, you can call it, it's a little bit more expensive oscilloscope, so you can set 10 byte worth of information as a debug trigger, as a trigger pattern. So this is the advantage. Now we'll go to my MSOS 804 and I'll show you there how does it look. That's the most capable oscilloscope I have, and how does it look different. You can look at the oscilloscope. It is updating quite fast. The update rate of the oscilloscope is quite dependent on the sample rate and sample depth. Right now it's sampling at 100 kilo samples, and sample depth is set to 1 kilo points, and I'll set it to automatic, and you see the signal is a little bit clearer, and its update rate is almost similar. It's definitely slower. Now I will switch to web view, or its VNC view, so that I can record better and you will see better contrast. So this is just to show you that what you view on the live oscilloscope and what you view on the screen is different. So we have a changing signal, and both RS232 and UART signal is also being displayed here. Same stuff, 5 volt UART signal. So we'll set up a decode. First of all, you need to set up a trigger, and then we will set up a decode. Let me zoom out or change the time base so that we can look for that trigger condition. You see, same trigger condition is also there. And let me enable the cursors. We can measure it on this oscilloscope as well. So I have set up a marker, and you see it says around 0.4 milliseconds. Okay, so same stuff which we did last time. We'll set up a pulse trigger on the channel 1, and you will be able to see how does the trigger stabilizes with it. Right now still this trigger is flickering all over the places, and we'll go to the trigger menu and set up a trigger. Same stuff, channel number 1, instead of edge we'll do pulse width, and positive going pulse width greater than around 3.8 milliseconds. Okay, and now it should be stable if our trigger is right. It doesn't look like stable because we are in auto mode. I'll go to trigger mode. Now it's stable. Okay, so I have decreased the time base. I have decreased the voltage per division for the channel number 2, and you can see it's a little bit different. It is at the time 10 volts per division, around 10 volts per division. Signal is 5 volt per division, and you can see the difference between the voltage levels for RS232 and UART. And now we will do a little bit larger capture. So now we will set up a protocol decode. We will do a setup protocol decode, and it's set for UART protocol decode, and we need only RX. Maybe you can choose the TX as well. Channel 1 word size is 8, parity, no parity, baud rate is 9600, and ideal polarity is high, MSP order is MSP, and the frame doesn't exist. If you want, I can set up a auto 0 or something like that, and now it should be able to decode. We'll do a single capture so that you can see it. What happened to my channel 1? Maybe I'll bring it down a little bit. Yeah, so 50. This is the displaying hexadecimal words, of course, and you remember after that there should be a 54 coming soon. I'll change the time base, and I don't see any 54. Maybe I'll see in the recorded window. No 54. Display format I changed to ASCII. Okay, it's not decoding for some reason. I do not know the reason, but it's not decoding for some reason. Okay, we are triggering good, but it's not decoding for some reason. Let's take a look at the protocol. I believe this MSP LSP is wrong. Yeah, this was wrong. Bit order is LSP first. So this is also a pitfall. Many oscilloscope allow you many features, and with many features you can have many mistakes. So you see Tektronix. Let's zoom out a bit even further so that we can see a little bit more packet. And you see Tektronix enabling innovation, I do not. Let's go to the settings and change it to hex, and we will look for this 0A and we will set up a framing there. Protocol decode hexa 0A, enter. Okay, framing has been enabled. Now we can change the display one more time as sky. So you see, same message appears: Tektronix engineering innovation, engineering innovation. If you want, we can set up the decode on the channel number 3 as well, just to show you. It will of course not detect because the polarity is inverted. Same stuff, same signal, just a different view. So we were able to manage to decode and find the trigger condition with this oscilloscope as well. We were able to trigger on the frames, we were able to trigger on the basis of pulse, and we were able to frame our packets. We can easily decode what we are looking at it. So we can easily find out what's the content of the packet. If you want, I can show you the setup trigger, the bus trigger as well, protocol trigger, RS232, and the auto setup. I do not care all that much. And it automatically got this Tektronix enabling innovation. I do not know how stable the trigger, it's not stable at all. So automatic mode does not find the stable trigger condition. We can define this trigger condition for it. Okay, and what should be the trigger condition? Trigger condition should be 5465. So you look at it, this oscilloscope allow you to number of words. Let's see how wide it can go. So it can go up to 27 words. We generally do not need that many words, even 1-2 bytes are enough. Okay, so this oscilloscope is more capable, does more things. I have set up a trigger to 5465 TE Tektronix, the first 2 bytes of Tektronix, and it's triggering right where it's supposed to. Everything is happy, frame is being displayed, Tektronix enabling innovations, and you see on your screen that it's working wonderfully. So there you have it. In this video I showed you how to decode RS232 and UART signal using 3 different oscilloscopes. As said, this is a series of video. In the next video, going to cover next protocol, and you will see there are multiple protocols coming soon. We will see CAN, and we will see LIN, and we will see many other protocols. USB will be coming, Ethernet will be coming, Flex will be coming, and MIL will be coming, and MIPI will be coming. MIPI and USB is going to be interesting at some point. PCI will be coming, and maybe I'll find out a target for USB 3.0 decode as well. I need appropriate setup for that, but I do not have appropriate probe. I only have one 4 GHz probe and 2.5 GHz probe. Maybe we can get away with 2.5 GHz active probes with this oscilloscope, because only this my big oscilloscope can decode USB or USB 3.0. My Tektronix MDO3000 can also decode USB LS and USB FS, but it cannot decode USB HS. My big oscilloscope can decode everything, and we will try to find out further. If you are interested in looking at the PCI or any other protocol decodation, keep watching, and I will get back to you soon. You can visit my website www.circuitvalley.com.